intense heat. The shockwave would travel across the globe, causing violent earthquakes felt thousands of miles away, toppling buildings and splitting the ground open. The impact would send colossal amounts of debris into the sky, creating a mushroom cloud of dust and rock that would darken the skies. The blast wave would flatten everything in its path, uprooting forests and leveling entire cities, with hurricane-force winds tearing through the atmosphere. As debris falls back to Earth, it would ignite massive fires, creating firestorms that would spread for hundreds of miles, consuming everything in their path. What if a Texas-sized...
If you need money now, there is...
What if we replaced Earth's oceans with sulfur dioxide, a toxic gas that is dangerous even in small amounts? Imagine entire oceans of it. Earth would become a death trap for most life. Sulfur dioxide would evaporate into the atmosphere, creating thick toxic clouds. The sky would turn a sickly yellow, and breathing would be deadly for all life. The evaporated sulfur dioxide would cause massive acid rainstorms, corroding buildings, killing plant life, and polluting the soil. The whole planet would become toxic. Marine life wouldn't stand a chance. Fish and other sea creatures would die almost instantly, as sulfur dioxide is extremely harmful to living organisms. Sulfur dioxide is also a cooling agent. It would reflect sunlight away from the Earth, leading to a drastic drop in global temperatures and possibly triggering a new ice age. With oceans turned to poison and temperatures plummeting, ecosystems worldwide would collapse. Most life forms wouldn't survive the toxic atmosphere and freezing conditions. Replacing Earth's oceans with sulfur dioxide would create a hostile, unrecognizable world, cold, toxic, and deadly to all life. What if we replaced Earth's ocean? What if a magnetar, the most powerful magnetic object in the universe, entered our solar system? A magnetar is a type of neutron star with a magnetic field trillions of times stronger than Earth's. Let's place it near Jupiter's orbit. Even at that distance, the magnetar's magnetic field would cause chaos across the solar system. Earth's magnetic field would be torn to shreds, leaving us exposed to deadly radiation. Satellites, electronics, and the power grid would be fried instantly. Even human biology wouldn't be safe. The intense magnetic storm could disrupt brain activity, making survival nearly impossible as the chaos deepens. Its gravity would destabilize planetary orbits, pulling some planets closer while flinging others far away. The stable orbits we rely on would collapse. Even the sun would feel the effects. The magnetar could strip away its outer layers, triggering massive solar flares and more instability in the solar system. A magnetar entering our solar system would cause total destruction, tearing apart magnetic fields, disrupting orbits, and leaving Earth uninhabitable. What if a magnetar, what if Earth had a second atmosphere layer? A second atmosphere would act like a protective shield, trapping even more heat and gases around the planet. But what would that mean for us? With an extra layer, Earth would become much hotter. The lower atmosphere would trap more heat, leading to warmer temperatures and more extreme weather everywhere. This extra heat would fuel intense storms, hurricanes, and stronger weather systems. Expect more violent and unpredictable weather year-round. But it wouldn't just affect the climate. The second layer might reflect light, creating a glowing sky at night, making stargazing impossible. Space travel would also become more difficult. The thickened atmosphere would create more drag, making it harder for rockets to escape Earth's gravity. The second layer might block some of the sunlight, affecting plant growth and reducing food production. Plants would struggle to photosynthesize with less direct sunlight. A second atmosphere could protect Earth, but it would also create hotter temperatures, harsher storms, and major changes to life as we know it. What if Earth had the same density as Saturn, the least dense planet in the solar system? Saturn's density is so low that it could float in water. If Earth had the same density, it would expand, becoming much larger than it is today. A less dense Earth means weaker gravity. You'd weigh much less, and jumping would feel easier. Sports would get more interesting. But with weaker gravity comes changes. Earth's atmosphere would spread out, becoming thinner. The air would still be there, but different. Our oceans and rivers would spread across a larger surface, becoming shallower. Climate patterns would shift. Life on Earth would face challenges as plants and animals encounter new conditions. Humans would need special routines to maintain health in lower gravity, similar to astronauts in space. Our daily lives would change in this expanded world. The planet's rotation might slow, making days longer. Seasons could change as the planet's tilt and orbit would be affected. The sky would look different too, with stars appearing brighter in the thinner atmosphere. What if Earth had the same density? What if a moon could be habitable without the warmth of a nearby star? In this simulation, we're exploring a scenario where tidal heating creates a habitable world beyond a star's traditional habitable zone. We have two identical objects, each 8 times the mass of Earth, orbiting on opposite sides of the Sun. Both are outside the Sun's habitable zone, with one remaining a frozen planet. The other object is a gas giant with a moon orbiting it. This moon experiences intense tidal forces from its parent planet, generating internal heat. This process is similar to what we observe in our own solar system with Jupiter's moon Io, which is the most volcanically active body we know due to tidal heating from Jupiter. We observe the moon's surface temperature is much higher than expected for its distance from the Sun. The powerful tidal forces from the gas giant are flexing the moon's interior, generating enough heat to maintain habitable conditions. Despite being far from the Sun's traditional habitable zone, the moon's surface is warm enough for liquid water to exist. We can see a mix of oceans and land masses, contrasting sharply with the nearby frozen planet. What if a moon could be habitable without the warmth of a habitable world beyond a star? What if we replace the Sun with a white dwarf and put Earth in its habitable zone? A white dwarf is the hot, dense core left when a star like our Sun dies. We're swapping our Sun with one and moving Earth closer to maintain warmth. To keep Earth habitable, we move it to 0.01 astronomical units from the white dwarf, 25 times closer than Mercury is to our Sun. At this distance, Earth completes an orbit every 10 hours and becomes tidally locked, with one side always facing the star. Let's speed up the simulation to see the long-term results. Earth becomes far hotter than we've ever known. The white dwarf's intense UV and X-ray radiation creates an alien environment. On the star-facing side, temperatures rise to extreme levels. The atmosphere thickens, creating a pressure cooker effect. Earth's vegetation disappears, unable to survive the harsh conditions. Even the dark side is surprisingly hot. Heat circulates globally, erasing Earth's familiar climate zones. The planet transforms into vast, inhospitable deserts or barren wastelands. Life as we know it couldn't survive here. Any hypothetical inhabitants would need incredible adaptations to withstand the heat, pressure, and constant bombardment of radiation. What if we replace the Sun with a white dwarf and put Earth in its habitable zone? What if we swapped Earth and Moon sizes? We shrink Earth to the Moon's radius of about 1,079 miles, while expanding the Moon to Earth's radius of about 3,959 miles. Earth's mass reduces to 0.02 Earth masses, while the Moon increases to 0.6 Earth masses. The Moon takes Earth's former orbit around the Sun, residing in the habitable zone. Earth initially orbits the Moon, but proves unstable. Within months, the Moon can't maintain its gravitational hold on Earth. Earth drifts away, settling into its own orbit around the Sun, close to the Moon's path, but distinct. The smaller Earth becomes completely inhospitable. With only 2% of its original mass, its gravity is too weak to retain an atmosphere or liquid water. The surface is exposed to harsh solar radiation and extreme temperature swings between day and night. Standing on this miniature Earth would feel like being on an asteroid. A person could easily jump miles high and potentially achieve escape velocity with a powerful enough leap. The horizon would appear much closer due to the planet's small size. Without air or a magnetic field, the sky would be black even during the day, with stars visible alongside the Sun. The enlarged Moon would dominate the sky when in view, appearing as an enormous disk. The enlarged Moon, despite its increased size and mass, still lacks sufficient gravity to maintain a dense atmosphere. What if we swapped Earth and Moon sizes? What if we increase the Moon's mass to match Earth's? We create a double planet system by equalizing the Moon's mass with Earth's. The Moon grows larger and becomes more spherical due to its increased gravity. The Earth-Moon barycenter shifts to a point between the two bodies. Both planets now orbit this common center of mass, completing a rotation every 11 days. Tidal forces intensify. Earth's rotation slows, with days gradually lengthening. The Moon becomes tidally locked more quickly. Earth experiences extreme tides, reaching miles in height. This increases coastal erosion and further slows Earth's rotation. Volcanic and seismic activity increases on Earth due to stronger gravitational stresses. The Moon becomes geologically active, potentially developing plate tectonics. Earth's axial tilt stabilizes, leading to more consistent seasons and affecting long-term climate cycles. The Moon appears larger in Earth's sky. Solar eclipses become more frequent and longer. This double planet system slightly alters the orbits of other planets in the solar system. What if we increase the Moon? What if we terraformed the Moon? In this simulation, we're transforming the Moon into a habitable world while maintaining its mass and orbit. First, we speed up the Moon's rotation from its 28-day cycle to a 24-hour day, matching Earth's rhythm. Then, we add a breathable atmosphere, giving the Moon a thin blue haze. Next, we introduce water, filling basins and craters. The Moon's appearance changes dramatically. now showing a mix of gray land and blue seas. We increase the magnetic field to match Earth's strength, helping to protect the new atmosphere. The moon now appears brighter in Earth's sky, reflecting more light due to its higher albedo. As the simulation progresses, the moon's surface temperature rises and stabilizes, thanks to the greenhouse effect of the new atmosphere. Despite these changes, the moon's orbit stays the same. However, the new oceans and faster rotation create more complex tidal interactions with Earth. What if we terraformed the moon? Did you know an asteroid named Apophis will pass incredibly close to Earth on April 13, 2029? It'll swing by at just 19,000 miles from our planet, closer than some satellites. When discovered in 2004, Apophis had a 2.7% chance of impact in 2029, later shifting to a 1 in 45,000 chance for 2036. Thankfully, further observations have ruled out any impact for at least 100 years. But what if Apophis did hit Earth? This 1,100-foot wide asteroid would strike with the force of over 1,000 megatons of TNT. The impact would create a crater several miles wide, causing widespread destruction for hundreds of miles around. If it hit land, it would trigger massive earthquakes and firestorms. An ocean impact would generate tsunamis hundreds of feet high, devastating coastal areas worldwide. The impact would also eject massive amounts of dust and debris into the atmosphere, potentially leading to a period of global cooling. This impact winter could last for years, disrupting agriculture and ecosystems globally. While not a planet killer, an Apophis impact would cause regional devastation and have long-lasting global consequences. Luckily, this asteroid is not going to impact Earth in the foreseeable future. Did you know an asteroid named Apophis will—
If your paycheck isn't for a couple of days—
What if we replaced our sun with a quasi-star and moved Earth to its habitable zone? A quasi-star is a hypothetical star from the early universe, so massive it contains a black hole at its core, yet still shines. These cosmic monsters could be millions of times more massive than our sun, dwarfing even UY Scuti, the largest known star. In this simulation, Earth's orbit around this behemoth takes a staggering 19,920 years to complete. The seasons in this new world are on an epic scale. Each season lasts for 4,980 years. That's almost 5,000 years of summer, followed by 5,000 years of fall, then 5,000 years of winter, and 5,000 years of spring. But here's the twist. At any given time, one hemisphere experiences summer while the other is locked in winter. The equator becomes a twilight zone of perpetual dawn or dusk, a narrow band of habitable land between extreme heat and cold. Imagine a world where half the planet is a scorching desert and the other half is a frozen wasteland, but between them lies a strip of land with Earth-like conditions, slowly moving as the planet orbits the quasi-star. Human civilization might become nomadic on a grand scale, following this habitable zone as it crawls across the planet over thousands of years. Cities would be built, flourish, and then be abandoned as the twilight zone moves on. What if Pluto were placed close to Earth? Let's move Pluto to just 186,000 miles from our planet and see what happens. Immediately, Pluto's presence causes dramatic changes. The moon's orbit around Earth begins to distort, as Pluto's gravity creates a chaotic three-body system. Earth now has two orbiting bodies competing for dominance. In the first few months, chaos takes over. Pluto's orbit begins to stretch out, but it continuously disrupts the moon's path. At times, the moon gets pulled far from Earth, and at other moments it comes uncomfortably close. Pluto and the moon even start crossing paths, nearly colliding at points, which only adds to the instability. As the months go by, Pluto's orbit becomes more elliptical, bringing it dangerously close to Earth. Meanwhile, the moon's orbit is completely erratic, far from its usual steady path. It strays so far that it could either crash into Pluto or be ejected from Earth's orbit entirely. On Earth, these changes wouldn't go unnoticed. Tides become unpredictable and extreme, causing problems for coastal areas. The extra gravitational forces might even trigger more earthquakes and volcanic eruptions. Earth's rotation could slow down, making our days longer and further destabilizing life as we know it. For nearly a decade, this unstable system persists, though it manages to avoid catastrophic collisions. Pluto's orbit becomes more defined, while the moon remains far from its original path. Earth continues to experience the chaotic effects of this gravitational battle. Then, after almost 10 years of delicate instability, everything changes. Pluto is finally ejected from the Earth-Moon system, thrown into a new orbit around the Sun in the habitable zone, leaving Earth and the Moon to slowly recover from the chaos it caused. What if Pluto were placed close? What if Earth were one of Mars's moons? Let's replace Mars's moon Deimos with Earth and see what happens. Earth's massive gravity quickly disrupts the Martian system. Drawn together by their mutual attraction, Earth and Mars collide in a cosmic merger of unprecedented scale. Phobos, Mars's other moon, narrowly escapes the initial impact. After speeding up the simulation and letting many years pass, we see the final result of this cosmic collision. A new world has emerged, taking up residence in Mars's former orbit. This planet, a fusion of Earth and Mars, presents a striking appearance. Vast ice sheets cover much of its surface, reminiscent of a global ice age. Between these frozen expanses, deep blue oceans span significant areas, hinting at the potential for liquid water. This new planet spins rapidly, completing a rotation in just 8.32 hours. Its year stretches to 22.2 months as it follows Mars's old path around the Sun. Despite its chilly average temperature of -88.2 degrees Fahrenheit, the planet shows promise for habitability. It scores 79% on the Earth Similarity Index and has a 66.5% life likelihood. Phobos, now the sole survivor of the original Martian system, orbits this new world every 1.38 days in an elliptical path. What if Earth were one of Mars? What if Earth's rotation slowed to 30 hours? As we slow Earth's rotation, the changes are subtle but profound. The most immediate effect is longer daylight hours, which has both positive and negative consequences. On the positive side, increased sunlight leads to enhanced plant growth. Forests become denser, and agricultural productivity rises. Solar energy generation also increases, providing a boost to renewable energy efforts. For humans, the longer day aligns better with our natural circadian rhythms. This could lead to improved sleep patterns and potentially better overall health. The extended daylight hours also provide more time for work and leisure activities. However, the extended day-night cycle brings significant challenges. The longer exposure to sunlight results in higher daytime temperatures, while the prolonged nights lead to colder nighttime temperatures. These temperature extremes create more severe weather patterns, including stronger storms and more intense heat waves. Ocean currents and tidal patterns are also affected by the slower rotation. This disrupts coastal ecosystems and marine life. What if we slowed down Earth's orbital speed from 30 kilometers per second to 20 kilometers per second? Earth's current speed keeps it in a nearly circular orbit around the Sun, crucial for our stable climate. By reducing this speed in our simulation, we disrupt the delicate balance between the Earth's velocity and the Sun's gravitational pull. As we decrease Earth's velocity, it lacks the speed to maintain its circular path. Instead, the orbit stretches into an ellipse due to the Sun's gravity. At its closest, Earth now swings dangerously near Mercury's orbit. At its farthest, conservation of energy ensures it reaches back to its original distance from the Sun, the point where we initially changed its speed. This new orbit is wildly unstable. Earth's speed fluctuates between 20 kilometers per second and 60 kilometers per second, completing a full orbit in just 6.4 months, half its usual time. But the orbital change is just the beginning. Each close approach to the Sun drastically increases Earth's temperature. This heat releases more water vapor and greenhouse gases into the atmosphere, trapping even more heat. A runaway greenhouse effect begins. With every orbit, temperatures become more extreme. The rapid climate shifts make agriculture nearly impossible. Coastal areas flood as polar ice melts, while other regions experience intense droughts. Earth's average temperature rises relentlessly. Oceans start to evaporate, further accelerating the greenhouse effect. The atmosphere grows thicker and more toxic. If this continues, our once habitable world could become a Venus-like inferno, far too hot and hostile for life as we know. What if we gave Mars Earth-like characteristics? Could we make it habitable? Let's start by adjusting Mars's atmosphere. We'll increase its mass to match Earth's and raise the number of atmospheric layers from 1 to 5, creating a more effective greenhouse structure. Now let's fast forward the simulation. As time passes, we see dramatic changes. The planet warms from -60 degrees Celsius to an average of 17 degrees Celsius, transforming Mars into a more hospitable world. Now, let's add water to Mars. We'll raise the sea level in our simulation. As we do this, we see oceans forming in the lower elevations of Mars, creating a water cycle crucial for Earth-like conditions. Mars's rotation and axial tilt are already Earth-like, providing similar day-night cycles and seasons. Next, we'll add a magnetic field to protect the new atmosphere and shield the surface from radiation. In reality, Mars can't generate this naturally due to its solidified core. Our transformed Mars now has oceans and clouds. It retains some unique features: 38% of Earth's gravity and a 687-day year. Olympus Mons, the solar system's tallest mountain, now stands surrounded by a Martian ocean. What if we gave Mars Earth-like characteristics? Could we make it habitable? Let's start by adjusting Mars's atmosphere. We'll increase its mass to match Earth's and raise the number of atmospheric layers from 1 to 5, creating a more effective greenhouse structure. Now let's fast forward the simulation. As time passes, we see
I gave my little brother $1.
What if we gave Venus all of Earth's characteristics? Could it become habitable? We'll start by speeding up Venus's rotation to match Earth's 24-hour day. This faster spin spreads heat more evenly and creates a magnetic field. Then, we'll tilt Venus's axis to 23.5 degrees, giving it seasons like Earth. Now, let's adjust the atmosphere. We'll reduce the atmospheric mass to match Earth's, eliminating the toxic greenhouse effect. Notice how the thick clouds start to thin out. This change significantly alters Venus's appearance, transforming it from a pressure cooker to a more Earth-like world. Look at that temperature drop. We're going from a scorching 460 degrees Celsius to a comfortable 24 degrees Celsius average. Much better. We'll add oceans covering 70% of the surface, just like Earth. The faster rotation gives Venus a magnetic field similar to Earth's, protecting it from solar wind and cosmic radiation. Our transformed Venus now resembles Earth, with clouds, oceans, and land masses. But would it be habitable? Possibly. With Earth-like conditions and a protective magnetic field, it could potentially support life. However, maintaining these conditions would be challenging, given Venus's closer proximity to the Sun. This shows us how many things have to be just right for a planet to support life, and why Earth is so special. What if we gave Venus? What if a negative luminous sun existed next to a regular sun? Imagine two stars locked in an eternal dance, one giving energy, the other constantly taking. The negative sun acts like a cosmic vacuum, absorbing light and heat from its positive partner at an astonishing rate. Any planets caught in this bizarre binary system would experience extreme conditions. As they orbit, they'd swing between scorching heat and unimaginable cold. One side of the planet would bake under the regular sun's rays, while the other would freeze instantly in the shadow of the negative sun. The regular sun, constantly drained of its energy, would behave unpredictably. Its usual life cycle would be thrown into chaos as the negative sun feeds on its power. The space between these stars would become a cosmic battleground. Powerful gravitational forces would warp space-time itself, creating a turbulent region where the laws of physics are pushed to their limits. Massive bursts of radiation might erupt from this cosmic struggle, sending waves of energy rippling across the galaxy. What if a negative luminous sun existed next? What if the sun's luminosity turned negative? This would mean our star actively cools its surroundings instead of warming them. Although mathematically possible, this doesn't exist and has never been discovered. In this scenario, the effects on our solar system would be dramatic. Mercury would freeze over almost instantly, its surface transformed into a barren, icy wasteland. Earth would face a catastrophic freeze. Oceans would turn to ice from the surface down, forming sheets up to 2.5 miles thick. That's about 9 times taller than the Empire State Building. Without sunlight, photosynthesis would cease within days. Amazingly, some deep-sea organisms near hydrothermal vents might survive, becoming the last bastions of life on our planet. Venus, with its thick atmosphere, would hold on to its heat the longest. Its powerful greenhouse effect, normally making it hotter than Mercury, would now work to slow the cooling process. While Venus would eventually freeze like the other planets, its dense atmosphere might allow it to remain warmer than its neighbors for an extended period, possibly for centuries. However, the extreme conditions and lack of water reserves on Venus mean it wouldn't experience a habitable phase during this cooling process. What if a star as big as UY Scuti replaced Saturn? This star isn't just big, it's colossal. With a radius about 1,700 times larger than our Sun, it dwarfs most of our solar system. Jupiter is gone instantly, swallowed by UY Scuti's enormous radius. Mars narrowly escapes at first, orbiting perilously close to this stellar inferno. The inner planets, Mercury, Venus, and Earth, face an unimaginable heat blast. Oceans boil away and atmospheres are violently stripped from planets. The immense mass of this giant warps the entire solar system. Uranus and Neptune are hurled into wild, unstable orbits. Our Sun looks tiny next to this behemoth, but the gravitational interaction between them is immense. As the simulation progresses, all planets eventually collide with the massive star, leaving no survivors. UY Scuti is a red supergiant in the constellation Scutum, about 9,500 light-years away. This dying star emits 340,000 times more energy than our Sun. It's in its final evolutionary stages, fusing heavy elements in its core. Eventually, it will end in a spectacular supernova, leaving behind a neutron star or black hole. What if a star as big as UY Scuti replaced Saturn? This star isn't just big, it's colossal. With a radius about 1,700 times larger than our Sun, it dwarfs most of our solar system. Jupiter is gone instantly, swallowed by UY Scuti's enormous radius. Mars narrowly escapes at first, orbiting perilously close to this stellar inferno. The inner planets, Mercury, Venus, and Earth, face an unimaginable heat blast. Oceans boil away and atmospheres are violently stripped from planets. The immense mass of this giant warps the entire solar system. Uranus and Neptune are hurled into wild, unstable orbits. Our Sun looks tiny next to this behemoth, but the gravitational interaction between them is immense. As the simulation progresses, all planets eventually collide with the massive star, leaving no survivors. UY Scuti is a red supergiant in the constellation Scutum, about 9,500 light-years away. This dying star emits 340,000 times more energy than our Sun. It's in its final evolutionary stages, fusing heavy elements in its core. Eventually, it will end in a spectacular supernova, leaving behind a neutron star or black hole. What if a star as big as UY Scuti replaced Saturn? This star isn't just big, it's colossal. With a radius about 1,700 times larger than our Sun, it dwarfs